Hello everyone. We are finally ready to create our first energy storage mechanism math model. The math model for elastic potential energy stored in a stretched or compressed ideal spring. Bit of review, right, that we've learned about ideal springs. We learned that ideal springs follow Hooke's law. Right, that the force exerted by a spring is equal to negative kx, right, where x is the elongation or the compression, and k is what is known as the spring constant of the spring. That's the slope of the graph, but it's also a measure of the elasticity or strength of the spring. It's how strong the spring is, usually in units like newtons per meter, or maybe at Home Depot it might be in pounds per inch or something like that, or pounds per centimeter. Right? But newtons per meter if we're in the SI system. These springs, the ideal spring is so intertwined with Hooke's law and the name of it that we even sometimes call these springs Hookean springs. Right? So a Hookean spring is one that follows Hooke's law. It's got a force and an elongation or compression that are proportional to one another, right? But always opposite in direction. So a graph of this equation would lie in either the second or in the fourth quadrant. I'm going to choose the fourth quadrant here just to have one that we can work with. In this case, perhaps we are stretching the spring to the right, so it has positive elongations, and then the spring is pulling back to the left, right? Negative forces. So that's why we're in the fourth quadrant. Now, how are we going to define the elastic potential energy? How are we going to define it graphically? What on this graph could we use as a measure of the elastic potential energy, the spring's ability to produce change because it's been elongated or compressed? Well, we need something here that works the way a spring works. As you stretch a spring further and further, what happens to its ability to produce change, or its elastic potential energy that's stored? Hey, it gets greater. Right? The more you stretch it, the more change it can produce. So what is there on this graph that gets bigger and bigger as you stretch the spring further and further? Some property of this graph that gets bigger and bigger as you stretch the spring further and further. Well, you might be tempted to say the slope, but notice the slope is actually constant. The graph is straight. But look here. There's another property of graphs that we used when we did motion graphs that come into play here with energy graphs as well. And that is the area under the curve. Do you see that as the elongation gets bigger, the area under the curve also gets bigger? Right? So perhaps we could define the elastic potential energy to be that. But we have one problem. Notice that this area is under the horizontal axis. Right? It's under the axis, and that makes it a negative amount of area. It doesn't really make much sense to me that you stretch a spring and so you have a negative amount of ability to produce change. Like, what would that even mean? It's not a vector. Right? It's just an amount of ability to produce change. So what would a negative even mean? So we need to get rid of that negative. And so we are going to define the elastic potential energy to graphically be the negative of the area under the curve of a graph of the force exerted by a spring versus its elongation or compression. The negative of that area, right, which turns it positive. Negative and a negative is a positive, right? So the negative of this area is the amount of elastic potential energy. And with the math that we already know and the labs that we've done in the past, we can now make a math model that fits that definition. Let us say we stretch a spring, a distance I will call x, at which point, according to the graph, the spring exerts a force, which we could call F sub s. Are you okay with that? Stretch a spring, x, it's exerting a force F sub s. Well, the area under this curve then is simply that. Now this is actually a calculus-y idea, just like slope is. But we don't have to use calculus for this because this is just a triangle. And we know how to find areas of triangles. In fact, we did a whole lab at it at the beginning of the year, right? We found that the area of a triangle is simply 1/2 its base times its height. So using that fact and what we have on the graph, we can create a math model. Now, the elastic potential energy is the negative of the area under the curve. So the elastic potential energy will be negative 1/2 times a base of, how big is this, the base of this triangle? It's x big, the elongation. The height of this triangle is f sub s. We're not done with it yet, because we know that if it's an ideal spring, and that's what we're going to deal with in here, we know that that force exerted by that spring is equal to negative kx, Hooke's law. So if we substitute that in for the force exerted by a spring, we get that the elastic potential energy is negative 1/2 times x times negative kx. Multiply things together, the negatives cancel, so we get a positive amount of elastic potential energy, which is why we made it the negative of the area under the curve. And x times x is, of course, x squared. So our math model for elastic potential energy is 1/2 spring constant times the elongation or compression squared. Don't lose that squared. It's very important that you keep that in the equation. 1/2 kx squared, as it more traditionally would be said. And so this is how we can calculate the amount of elastic potential energy. Or we can do it with a graph, right? The negative of the area under the curve. But this is a little handier, right, to be able to use mathematically. So it's our first math model for one of our energy storage mechanisms. And we will get math models over the next few days for our other energy storage mechanisms, so that we can eventually, and even work, so that we can eventually solve problems. Since we have our first energy storage mechanism, we now for the first time need a unit for our ability to produce change, right? An amount of energy stored. We haven't had one before, right? So let's get it right from this equation. K is the spring constant. That is the slope of this graph. So what are its units? It's the slope of the graph. Slopes are rise over run. So this would have units of newtons per meter. X is the elongation or compression. So that would be in meters. And don't forget, it's squared. So the meter on the bottom cancels out with one of the meters on top. And we are left with Newton meters of energy. But you may be saying to yourself, I have never heard of a Newton meter of energy. And that's because scientists decided that it was such an important little combination that they gave it its very own name. It becomes a derived unit, a combination of other units. And they decided to, instead of saying Newton meter, that they would name it after the guy credited with the discovery of the law of conservation of energy, James Joule. Right? So 1 joule of energy, notice it's denoted by a capital J because it's named after a person, so it's capitalized. 1 joule of energy is equal to 1 Newton meter of energy. Now I know that that's a little hard to understand by itself, but as we use it, right, you might be able to get into your head what a joule actually represents. 1 Newton over a meter, okay? Newton's not a very big amount of force, right? So this isn't really that much energy in a Newton meter, okay? So, by the way, remember that a Newton is itself a derived unit. It comes from Newton's second law, F equals ma. 1 Newton is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. A Newton is a kilogram meter per second squared. So a Newton meter, or a joule, is actually a kilogram meter squared per second squared. And you sure don't want to be walking around talking about energy that way. Right? Oh, this stretch spring has 10 kilogram meters squared per second squareds of energy. Right? Instead, you could say, hey, there's 10 joules of energy. Right? So this is a new unit for energy. It's a new derived unit for energy based on newtons and meters. So let's get a little more intense with this. What if instead of starting with no stretch and stretching to a distance x, what if instead it was already stretched a little bit, and we'll call that x sub I for initial, and then we stretched it a little further, x sub f, or final. Yeah, I don't know why in energy we use I and F for initial and final, but in motion we use O and nothing as subscripts. It's just the way it's done. So this is your initial stretch to your final stretch. How much energy did we store while doing that? Instead of going from 0, right, we started with a stretch and stretched it a little further. How much did the elastic potential energy change? Well, graphically, that would be the area under the curve from xi to xf. If you get my notation here, it's kind of a calculus-y notation. So it would be the area, that technically the negative of the area, right, between xi and xf. It would be that area. Now, we don't need to use calculus on that area, right? We could break it up. We dropped a little horizontal line right here. We could break it up into a rectangle and a triangle, and we could find those areas. A little tougher than just a single triangle or a single rectangle, but, you know, we could add them together. But I want to approach this from a slightly more calculus-y way, because I think it's instructive. Another way to do this is we could take the area from 0 to xf, and by that I mean this big triangle, right? And then subtract off the area from 0 to xi, the little triangle, and look what we have left, the area in between. Let me show you that again, all right? It's a little weird. No, it's a little different way of looking at things. So if I want to find the elastic potential energy stored in stretching the spring from xi to xf, I need to find the negative of the area under the curve from xi to xf, which is that. I could find this shape, right? Or I could find the area from 0 to xf, the big triangle, and subtract off the area from 0 to xi, the little triangle. Now, besides that being a second semester calculus idea, it helps us because we already know how to calculate the area of a triangle on this graph, right? We just did that. We know that the area of a triangle on this graph is 1/2 kx squared. So the area from 0 to xf, the big triangle, is 1/2 kxf squared. And the area of the little triangle is just 1/2 kxi squared. If we subtract those, right, we find how much the elastic potential energy has changed, right, in stretching it. And really, this is just final minus initial elastic potential energies. Right? I mean, that's how you find the change in anything. You take its final value and you subtract off its initial value. So, again, this kind of allows us to find this just by basically doing two triangles, right? Instead of doing I don't know, what is that, a trapezoid or something like that, right? Not to mention, it's kind of calculus-y for those that have had enough. Now, don't worry, all right? In this class, in honors physics, we are not going to do any functions that are more complicated than this. All right, so we never need to use calculus in here. We're always dealing with areas that are either rectangles or triangles. All right, so we're good to go. But in APC, you know, we do expand this into a calculus-y area. Now, for those of you that have some calculus, and by the way, if you're not in calc right now, don't worry about this. Don't take notes on this, right? In fact, you can turn off the video right now and just go on your merry way, right? But if you've had a year of calc, watch this because it's just kind of interesting to see how the calculus works here, right? So if we're going to use the calculus to do this, okay, we could say that the change in the elastic potential energy is the negative of the integral of the force with respect to stretch from xi to xf. Isn't that the same thing, right? We said the elastic potential energy was the negative of the area under the curve of the force exerted by a spring versus elongation or compression graph. Well, that's what this is in calculus, right? It's the negative of the integral of f of s dx from xi to xf. And from Hooke's law, we know that f of s, the force exerted by a spring, is negative kx. The negatives cancel. K is a constant, right? So we are left with the integral of x with respect to x, which I hope you know is just 1/2 times the constant times x squared, using the power rule, evaluated from xi to xf, which is, of course, exactly what we got before, right? Analyzing the graph. So why do I do this? Well, I do this, A, to show you that the calculus works, but B, I also want you to understand the fundamental theorem of calculus here, right? That you understand where this comes from and why we do integrals evaluated from the upper limit minus the lower limit. Because graphically, what we are really doing is we are evaluating the big triangle and subtracting off the little triangle, right? We are taking the whole area and subtracting this off. We are evaluating this function from the final value and subtracting off the initial value. Right? That is the calculus of this situation.